Hi and welcome back to the Low Level Devel channel's Gameboy Emulator development series. In the previous video we kind of finished up the CPU instructions, and now in this video there's a couple of bugs I want to fix that I found along the way, and I want to implement the timer so that we can go through and test our CPU against some of these, they're called Blargg Game Boy tests. They test all the different parameters of the CPU, making sure the flags are set correctly, making sure all the results are proper, and everything like that. So we'll run through. We'll of course first make some of these small fixes to change things, and we'll also implement a small little debugger, because those Blargg tests actually will output some data to the serial port, so we can create an I/O section to start reading data from the serial port just for the purpose of these tests. So let's get started. First, there's a couple of instructions I actually just forgot to add to this instructions.c, so I'm going to go ahead and add them, starting with this DAA, which is 0x27. Let's see, 2F, there is a CPL, 37 is SCF, and 3F is CCF. I think those are just the ones I forgot to add, and then there's a couple of small changes in the addressing modes. Let's see, starting with C6, this addressing mode should actually be AMRD8. Okay, that's just a small fix for that. And D6 should actually be, the addressing mode should be AMRD8 instead of just D8. And we want to put the register type A in there. And let's see, down to E6, this one should also be AMRD8 and register type A. Let's see, yes, and E9 should be addressing mode just AM_R, so not MR but R. And EE also RD8, register type A. Let me see, was that the last one? No, this OR. So F6 should be RD8, register type A. And FE, RD8, register type A. Okay, so that fixes all the issues in the instructions.c file, just a couple things we messed up along the way. Okay, so let's go on to, I actually want to make some changes to the lookups here. So instead of just using the instruction name, I'm going to use this register type lookup, which is, you know, none A, B, C, D, E, H, L, and all the way through all the register types. And I'm going to paste in a function here to essentially convert an instruction to somewhat of a disassembled version of it. It's not 100% accurate as far as what the disassembly is, but this is a kind of a good start. So this takes the context in the string. So initially we're just printing the name to the string, which, so for implied it's going to use the name. So register RD8, and I'm just kind of zipping through this real quick. So for instance, AMRR takes 2 registers separated by a comma. Let's see. Yeah, for instance, HLI has the instruction name, and then HL plus, and then the next instruction. So you can kind of just take this as if for some reason I missed one of them, it should hit this invalid AM down there. But I'm just kind of pasting this here. It's pretty simple. You can go through it if you want to, but I'm not going to cover it in heavy detail. This is just kind of to make the logging a little easier and easier to understand what's going on. So let's see, I'll paste this inside the CPU.h so I can use it in the CPU.c. So down here where we normally are doing this logging, it's going to create another character array. Call it inst. Maybe 16 should be big enough for it. And now I'll call that function to convert the current instruction to that name. So inst to stir, passing in the context address and that str. Okay, so now I just need to put that in place of this, and I'm going to make this 12 for the length, and I can replace this inst name with that string. So this is just kind of some improvement of our logging. So let me go through and let's see, build, make clean, make, oh, I messed up something here. I'm just going to recreate this build directory. See, make dot dot, clear and make. Okay, so now I can run it one of our tests, or I'll just maybe run this one. Now run the special, so you can see it's running through. Now if I close it out, you can see actual instructions. This is what your code would look like if you're actually building this code for one of these games. We have the CB instruction, there's the JR, which would jump 10 hex, LDEA, load A into E, so load the address of HL into D, some push AF, push BC. So this is just kind of a utility method to make this code a little more readable in our log. So now that we're past that, let's go into create a new file here called io.h, and this is going to be for handling our IO reads. I'm just going to copy and paste this stuff because I just want an IO read and an IO write. If you remember, those are in a certain range in the bus. So let's save that. So now I'll create an io.c, include that io.h. Let's take these functions. Okay. So there's only a couple IO devices we're going to process in this one. So let's start by including this io.h up here. So if you remember, our IO range is down here somewhere. Yeah, right here. So I can kind of copy this code and I'll say return IO read address. Okay, and now go into here. I'll just paste that into there. So right now, as of this time, it would behave exactly like it did before. So and we'll say IO write address value. Okay, and paste that in here. So now there's a couple of specific addresses we want to handle. That'll return 0. So some of these addresses, I think, should we start with this serial, just because those Blargg tests will write data to serial. I'm first going to create a small array here to hold data from the writes. We'll call it serial data. It's just 2 bytes. And so let's look at the this serial data transfer section of the pan docs. So looking in here, if the address is FF01, that's the serial data transfer. FF02 is the serial transfer control. So FF02, certain bits are set. That means data is available or ready to be written. Like bit 7 means that 1 is a transfer is in progress or requested. Bit 1 that's Game Boy only mode. Bit 0 is whether you want to use an internal clock or external clock. That isn't too important right now, but the Blargg tests will set some data in there letting us know that we can read data from the serial interface to start using. So I'm going to start with checking if the address is FF01. Then we're going to return serial data 0. And likewise, if it's FF02, we'll turn serial data 1. And we can actually copy this into the right section. So serial data equals value, then return, and then the same down here, but serial data 1. And then if it falls through, then we still hit that unsupported bus write and unsupported bus read. Okay, so now that we have that set up, let's go and we'll create a dbg.h. So this is a little section of code for debugging for those Blargg tests. It's not going to be useful in pretty much any of the normal ROMs, but it'll be useful when running these Blargg tests. So I'm just going to include comment. Let's see. So I have a couple of functions. We'll say dbg underscore update. I think we might need CPU context in there, not sure off the top of my head. Probably not actually. So we have dbg update, and then we'll be getting any updated characters, and then dbg print. So if we have any characters, printing them. Alright, so I'm going to include cpu.h. And yeah, it looks like we don't need these. Okay. So I should copy those and put them into a C file. Let's call it dbg.c. So what we will need is bus.h, I believe. But actually, let's first create we're going to create a 1K string. So this will be updated based on data we get from this Blargg ROM when it's writing to the serial. And the size of the current message is 0. We'll just build it up once we get new characters. Okay, now we added bus.h. So now if bus read, and remember FF02, that's the control. If it equals 0x81, meaning the top and bottom bits are set, then we can read data from FF01. That'll give us a character. Okay, so now once we're done reading that character, we're going to say debug message at message size plus plus equals that character. And then we want to bus write to FF02 the value 0. So we reset those flags so we don't keep reading the same character over and over again. And the Blargg test will reset that flag when it's ready to. Okay, so now as far as printing, we'll just say if debug message at 0. If it's not 0, then there's something for us to print. So we'll just print it out, dbg %s and dbg message. Okay. It's pretty simple actually. So now let's go to cpu.c and let's see, I want to do that somewhere up, yeah, maybe down here after we print out the debug data for the instructions. That's where we'll update if there's any update to the characters, and print the debug message. And we'll include dbg.h. So let's make that, and actually now if we run this ROM, this 01 test ROM, you see that message there, dbg 01 special, that means that test is running, and eventually it should have an error, or it should say passed. So just let it keep going, and you might want to run these offline. Oh, there you go, passed. So now so this is all the text that was output to the serial console by that test. So we know test 01 in ROMs passes. So let's see 02 interrupts. So that one fails actually. And I think the reason that failed is actually because we haven't implemented a timer yet, and interrupts test really needs a timer for it to work properly. Okay, so actually let's go ahead and just start the timer. A couple things we have to do firsthand. Let's see, the CTX ticks ++, we need to take that out of that main loop, because that's not really how we calculate those cycles. We want to actually implement this EMU cycles now. So first of all, for every CPU cycle, we need to tick the timer 4 times. So we're going to loop I to N and tick that time. Well, we'll set the EMU ticks that many times, and we're going to call a function called timer tick. It's something that we will implement soon, and add timer.h. So let's go ahead. If you remember, I had these already there as a starting point, the init and the timer tick. So now we can actually work on implementing them. Oops. So actually let's add a structure. This is the timer context, and these are actually registers, memory mapped registers, which you'll see, which I'll show you later. But so div is actually related to, if we go down here, timer and divider registers. So div is the divider register. There's some details about how you deal with that register here. The TMA, the TAC, and the TIMA. Those are all right in here. So I've just created a simple register for each of them in the timer context. So now in timer.c, let's start actually first we need to include interrupts.h, and we'll start our implementation. So we have our timer context that we're creating. By default, everything is 0 there. Now in our timer init, we want to set the divider to 0xAC00 when the timer is initialized. That's its default value. Actually, I'll put timer init inside this CPU run as well, so it gets called correctly. So in our timer tick, we're going to get the previous value of div, put that in a temporary variable, increment the div, And now we have this flag on whether we need to update the timer or not. So timer update equals false at first. Okay, so now we have a switch statement on this TAC. We're switching the bottom two bits. So checking those bottom two bits. In the case of 0, 0, so that's in the case that those two bottom bits are unset, the timer update flag will be set as such. So the previous div, grabbing the 9th bit, if the 9th bit is set on the previous and the 9th bit is not set on the new value, that means there is a timer update and will break. And we're going to do this for each of the 4 values. And if we look down here at the TAC, this is where it defines that. So, bit 2 means the timer is enabled. Bit 0 and 1 are those bottom bits that we care about. So in the first case, we're doing this 0, 0, which is the clock divided by 1024. The next one will be by 16, 64, and 256. So taking that 9th bit and checking its changed value is essentially how we divide by 1024. So I'm going to do each of these. So with 1, that bit that we check is 3. With 2, that bit that we check is 5. And then 7. So that changing of that bit is what triggers that, oh, we need to update the timer. So now if we do need to update the timer, and, well, yeah, and if you remember TAC and 1 shifted over by 2, so that second bit means it's enabled. So if the timer is if we do need to update the timer and the timer is enabled, we just increment that TIMA value. And if the TIMA value is hit 0xFF, that means that we need to reset it to the value that's in the TMA register. And then we need to request an interrupt. And hopefully that makes sense to you. If not, in the Discord channel, feel free to ask questions about this. I can kind of explain it in more detail. So now that we've implemented that timer tick, we need to add the timer write and the timer read. So with the timer write, we're switching the address. We really just need to handle these couple of different cases. So FF04, that's the div. In that case, whenever you write to FF04, we reset div to 0. Now FF05 is the TIMA. Whenever you write to that, we just set it to whatever value you're writing at. And that's the same with the other registers. The only one that's different is that divider register, because whenever you write to that, that's just a trigger for the CPU to reset that div register. So TMA and TAC. And then timer read is going to be similar to that. So let's see, U8 timer read address. So again, we're going to switch the address. In the case of 0xFF04, that's the div. We'll return ctx.div, shifted over by 8. And that's just the way the specification works, because we only care about that top value, the top byte. Yeah, top byte of the div register. So for 05, that's the TIMA. 6 and 7 is TMA and TAC. That's all there is to the timer. Pretty simple, huh? Okay, so now that we have this timer, did we add it to... Oh, we also need to include this timer get context. Okay. Yep, I think that's all we need to do for the timer.c. So now we can move on to the bus.c. Actually, not bus.c, the io.c. So if you remember, we checked FF01 and FF02. This time we're going to use between, if between. So if the address is between FF04 and FF07, we're going to call timer read. If you remember, between is a macro we added in the common.h. It's just to make the code a little more readable. And another special one, if it's FF0f, that's supposed to return the int flags. So let's see. Yeah, FF0f is the interrupt flag. So it has a flag for whichever interrupts are in the queue to be processed. So let's take this and we kind of convert the same thing over to the right. So this would be timer, yeah, no return there. Timer right, and put the value in there, and then return. And this one we'll call CPU set int flags with the value, and return. There we go. So now our timer should be working since we implemented those EMU cycles everywhere they're supposed to be. The timer should automatically now be getting updated whenever it needs to work properly with the CPU. And now going back to the CPU, I'm going to actually set the default values for everything correctly. Let me get rid of all this initial set. Just going to paste in. So the program counter is 100 again. Stack pointers, default, the A and F register, the B register, C, D, H. These are all the default values for those registers. These are all 0 and false by default. And whenever you reset the CPU, we're setting the timer div to A, B, C, C. Okay. So let's see if there's anything else I'm missing here. Yeah, I think we should be good. So let's do a make. Let's see, some CPU request interrupt. Oh, I forgot to add that. So let me go ahead and add that function. And we're just adding it right here in the CPU.c file, ORing the value for int flags with the requested interrupt type. Let's clear and make that again. Okay. So now if we run our O2 interrupts, let's let that run for a little while, and passed. Alright, nice. So that one is passed. So far our test 1 and our test 2 have both passed. So let's try a couple more. So I believe it goes to test 11. So O3 is certain opcodes. So we'll let this run. So that's opcodes SP and HL related opcodes. See, E8, E8, that means there was some issues with those in that specific instruction, and we see failed. So E8 failed. And so actually I did some debugging. So if we go back to our instructions, looking at E8, so E8 is the add instruction. Let's see, E8, yeah, add SP R8. So going back to there in our CPU proc, So let me just look for add. So in that special case down here where the register type is SP, see that there's one thing that I missed down here. So when checking the C flag, see the H we do greater than or equal, all those. The C flag was using greater than, so if I make that greater than or equal, then the flag should be set properly after that instruction. See, this is why these are good tests. They actually test all the different scenarios, whereas, you know, that looks like that might succeed, but certain values, if it's not set correctly, this will fail it. So there we go, you have it passed now. Okay, so test 3, the test set 3 is passed. Test set 4 is some of the immediate instructions, op R immediate. There's actually documentation for these tests that say exactly which of the instructions they do all the testing on, but you know, there we go. This one passed as well. Yep, help RM passed. So now let's do 5 RP. Not sure. So we can actually run this with no hup and put an ampersand at the end. If you do that, it'll run in the background. So now we can tail no hup.out and we see, oh, passed. So this is one way to not have to wait for all the scrolling text. You can run it in the background, it writes everything to a no hup.out file, and you can just tail the bottom of that no hup.out file to see what the output is. So I'll do that with 6 as well. I'll tail no hup.out, and you see 06 LDRR passed. Okay, let's try that with 7. So you can see this is the JR, jump, call, ret, RST, and all that. Tail no hup.out, it's still running. Now it says passed. Okay, so that one passed. So far 1 through 7 have all passed after some changes. So let's see. Change this to 8. MISC instructions. And that passed already. Okay. Hopefully you're following this. I'm just kind of running each of these individual tests, which will all give us indicators whether it's succeeding or not. And I'm running these in the background so I don't have to wait for the text. Okay, that one passed, so 09 passed. So we have 10, which is the bit operations, like those CB instructions. That one might take a little while. See, it's still running. Tail no hup.out. Oh, now we go. We have passed. So that passed. So we have 11 is the last one. Op related to A and HL. Still running, still running. This one's a longer running one. And passed. Okay, so it looks like all the Blargg tests have passed on this CPU code, which is a good thing. Now, if you look at this no hup.out file, it's 6.8 gigabytes. So letting it build up, you need to be careful because we're outputting a lot of data to the log. So you only output really what you need, but for right now, since we're debugging, it's a ton of data. So let me even just run this one by itself after I delete the file. If I close it, and now look at the size of it, it's 610 megabytes. So yeah, you need to be careful running this too long with all the debug if you're outputting it to a file. So that's primarily it for the CPU. We're pretty much done with implementing that. We might have to come back to it here and there, but from here on, we're mainly going to be concerned with some of the changes to the bus and different I/O devices we need to interface with, and then of course the PPU for displaying pixels on the screen. So that'll be probably where we'll start next, which is going to be quite a big endeavor itself because the PPU is not overly simple. It's not that complex. It's not as bad as the NES one, but you know, it is a little complex. So we'll do the next couple videos on that. And I hope you enjoyed this, and please like, comment, subscribe, and thanks for watching.